So today we're starting the topic of halogenoalkanes. Okay. So halogenoalkanes are those organic compounds in which one or more hydrogen atoms are replaced by halogens. Now what are halogens? Halogens are group 7 elements that are fluorine, chlorine, bromine, iodine and so on. So when you replace one of the hydrogens, at least one of the hydrogens from an organic compound, that becomes a halogen, that is a halogenoalkane. Now halogenoalkanes can be categorized as primary, secondary and tertiary, like the one we did in primary carbocation, secondary and tertiary. Okay, same concept is applied here. So you always have to look to the carbon to which the halogen is attached. Okay, if that carbon has two hydrogens attached to it, and on the left side you are seeing R means the alkyl chain, that is rest of the carbon chain. Okay, but you always have to look for the number of hydrogens in that carbon. So if it has two hydrogens, then you would consider it as a primary halogenoalkane. Then for the second one, you have to, if it has one hydrogen, then it will be a secondary, and if it has no hydrogens, then it will be a tertiary. क्या हो गया? जाओ भाई यहाँ से
ऑर्डर
अभी।
करो ना, पराठे अम्मी कह रही हैं।
परीसा भी जिंदा है वहाँ पे शायद।
खैर मुर्गी
हट जाओ भी, हट जाओ, मैं क्लास ले रहा हूँ, हट जाओ भी।
तुम्हारे कौन लाएगा?
अभी मैं 2 बजे ही जाऊँगा अगर यहाँ भी मैं।
फिर 2 बजे ही ऑर्डर होगा।
जाओ भाई, तंग करना है तो सुबह सुबह।
नहीं, ऐसे नहीं होगा।
Okay, so it will be a tertiary halogenoalkane. Did you got the difference in between them? Okay, you always have to look for hydrogens. Yes. Yeah, you'll always have to be concerned with the hydrogen group. Okay, always look whether that carbon has two hydrogens, one hydrogen, or none. Then I did some namings here. So when we are attaching now a halogen with a straight chain, we just call it with the name of the halogen, that is chlorobutane, okay, bromobutane, iodobutane. Butane will be the chain of carbons, okay. But if you are attaching the halogen in between the carbon chain, then it will be numbering, okay, like it's 2 bromo, then the carbon chain is of 3 carbons, that is propane. Similarly, I've drawn a skeletal formula in which I have 2 carbons to which 2 iodines are attached. So it will be 1,2-diiodoethane. Di means 2. Okay, these are some of the namings. Clear? Moving on to the physical properties of halogenoalkanes. Halogenoalkanes boiling point. Okay, so halogenoalkanes boiling point increases as boiling point of halogen increases as molecular size increases. It is because there are more electrons in larger molecules and more temporary dipoles, resulting in stronger van der Waals forces. Okay.
हेलो मैम श्याम जी, अमजद भाई आप आ गए? मैं आती हूँ ओके। मुझे दिखता है
So look into the graph. Okay, as we are increasing the carbon chain, the boiling point are increasing, and within the organic molecules, that is chloride, bromide, iodides, the boiling point is also increasing. Okay, so there are the same reason behind it. The number of electrons are increasing, which depends on the van der Waals. So the van der Waals will become more stronger. Okay, and more temperate dipoles. Clear? One more concept, that primary halogen alkanes have more boiling point than secondary or tertiary because they have greater surface areas, so stronger van der Waals forces. Okay, if I have bromopropane and 2-bromopropane, both will have different boiling point due to surface area. Okay, that is the concept here. You have 3 carbons, then you have Br here. Okay, this will have a greater surface area compared to, like if I make it the Br should be here, or it should be here, and so now the contact to contact surface, okay, carbon to carbon contact surface, one has been reduced because you have placed Br on that side. So now the hydrogen is on the backward side. That is why the contact, 2 carbons will make the contact, the van der Waals forces with the neighboring particle, and in this one 3 carbons will be making van der Waals forces. Okay, so that is a concept. Moving on to the next one, that is solubility. So halogen alkanes are soluble in organic solvent and insoluble in water. The reason is quite simple, because they cannot form hydrogen bonds with water. Okay, because forces are the reason behind the solubility. So they won't be forming hydrogen bonds, so they are not soluble in water. Instead, they will form van der Waals forces with other organic molecules, so they are soluble in organic solvents only. Okay. Mhm. Okay, now looking into the graph, we see the carbon to fluorine bond energy is highest, then chlorine, then bromine and iodine. What does this tell us? That fluoroalkanes, okay, alkanes, the organic compounds in which fluorine is attached, they are least reactive, while iodoalkanes are most reactive because less energy is required to break the Ci bond. Okay, so halogen alkanes perform one sort of reaction which we call it as nucleophilic substitution. Okay, nucleophilic substitution. One substitution we have already studied, that is free radical substitution, in which what was happening, that free radical was getting substituted, was getting replaced by hydrogen. Okay, we were replacing one hydrogen and we were substituting a free radical end. This time we will be substituting one nucleophile instead. So substitution of an atom by a nucleophile. Now what is nucleophile? It is a species. Species means it could be an ion or a molecule. It is not necessary that it will always be an ion. Okay, so it is a species which is strongly attracted to a region of positive charge. So nucleophiles have plenty of lone pairs, at least they have one lone pair. So they are always negatively charged. Okay, they have the negative effect. So they get attracted to a region where are there no electrons. Okay, where there is a need of electrons, they get attracted to that region. So that is obviously that is a positive charge region. Okay, so they get attracted to it and finally they get attached to it. So we have some examples. OH ion, hydroxide ion. Okay, oxygen has three lone pairs, so it is a quite stronger nucleophile. Cyanide ion, you have water. Okay, water itself is a nucleophile because it has lone pairs. Ammonia has lone pairs because it will be a nucleophile. So these are some of the examples of nucleophiles. Is it clear? Okay, so basically you have two mechanisms of nucleophilic substitution. One is SN1 and another is SN2. We call it SN means nucleophilic substitution. Okay, the N and S are in the wrong order, but it is SN, okay, 1 and 2. So in SN1 you always have to remember which sort of halogenalkanes will be reacted tertiary. Tertiary will undergo nucleophilic substitution number 1 always, and SN2 primary halogenalkane will always be going under. And what about secondary? They will use both. The examiner will tell you that which substitution to follow if it is a secondary. If it is a primary or tertiary, he won't be telling you, you just have to identify it by yourself. Okay, clear? SN1, first we are discussing SN1. SN1 happens in two steps. So the first step, we call it as a slow step. It is a rate determining step. Okay, RDS. It is a slow step. So what happens that the carbon and the Br, okay, the carbon gives it lone pair to the Br and Br gets separated. Okay, so why it is a slow reaction? Because it is not easy to separate the Br from the carbon. So that is why it is a slow, and it is a rate determining step. Okay, we will study in A2 chemistry that rate determining steps are the slowest ones because we need to determine the rate. If the step is slow fast, how you going to determine the rate? Okay, so that is the RDS step. So the Br gets separated, okay, with the lone pair, and this becomes a carbocation. Now this is a tertiary carbocation. So what happens in step 2? The OH, that was a nucleophile, then is attracted, okay, because it is always looking for a region of positive charge. So it looks for that region, the carbocation is there, and then it swiftly, okay, fastly, it just get attracted to it, okay, without any delay. So that is why it is a fast reaction, because they are just attracting to each other and it becomes an OH ion. So that is the whole basic simple mechanism of SN1 mechanism. Okay. Moving on to methyl. Okay, we can do this question. C. Good. Okay, this one. Okay. Then you have to draw it. Then you get to know of it. It's quite simple. You can literally look at the products to see that if the chlorine was on the second carbon, then where the could have the nucleophile be added. Which one? Oh, yes, the answer is A. Okay, what about this one? Okay, so in this one, we need only at least it to be one element that breaks down easily to form a precipitate. Okay, all the form a precipitate, fluorine, chlorine, iodine, all forms precipitate. But we need one compound in which there's at least a single element that quickly form the precipitate. Sorry, reactivity. No, it should be at the highest reactivity. It should be so much reactive that it breaks away easily. Okay, we need to break the iodine, fluorine, chlorine from the carbon. Okay, then it will form the precipitate. So chlorine is can form precipitate. Fluorine is least reactive. Okay, it won't be. Iodine is most reactive, and bromine is on the third one. C would be the correct answer because in C we can see we have iodine, so it will quickly form the precipitate. Okay, we had to see the quickest. Clear? Then we have Okay, what could be the answer? Leave the SN2, it is, yeah, it is B. Then moving on to, okay, this one.
क्या अब क्या मसला है?
चाय है।
ये ले जो
तार हटा दो यार, फिर परिसर होएगी, चार्ज नहीं था। लगा के नहीं चल रहा आउट मेरे। Yes.